Hey everyone, and welcome back to the channel. This is the second part of our video tutorial series on building a low-cost autonomous robot using two repurposed self-balancing scooters. In the first video, I covered the mechanical design of the robot, explaining its structure and assembly. In this video, I will discuss the electronics design, including the components used and how they are integrated. For raw setup and autonomous navigation, stay tuned for upcoming videos, where I will cover software configuration, sensor integration, and autonomous control. These will be posted in the coming days, so make sure to subscribe to the channel and hit the like button so you don't miss out. Let's get started. Wheeled robots move in two main ways: linear motion, where they travel forward or backward, and rotational motion, where they turn clockwise or counterclockwise. Their movement depends on the drive mechanism used. Differential drive robots have two independently controlled wheels that enable both movement and turning. Skid steering, often used in tracked vehicles, turns by varying the speed of wheels on either side. Ackerman steering, similar to a car, pivots the front wheels while the rear wheels provide propulsion. The type of wheels also affects mobility. Standard wheels support basic movement, while Mecanum and Omni wheels allow omnidirectional motion, enabling robots to move sideways without rotating. Our robot is a four-wheel differential drive system, where each motor is individually controlled. The base utilizes skid steering for turning, making it highly maneuverable. When all four motors rotate in the same direction at equal speed, the robot moves in a straight line, assuming there is no wheel slippage. Rotational movement is achieved by driving the motors on one side in one direction while the motors on the opposite side rotate in the reverse direction. This creates a torque around the robot's center, enabling it to turn in place. This design provides a balance between simplicity, efficiency, and robustness, making it well suited for various terrains and applications. For motors to rotate in both clockwise and counterclockwise directions, the direction of current flow needs to be reversed. In simple terms, this means that the battery wires connected to the motor terminals must be switched to change the direction of rotation. In electronic circuits, this switching is achieved using power transistors such as BJTs, bipolar junction transistors, or MOSFETs, metal oxide semiconductor field effect transistors. The most common circuit used for this purpose is called an H-bridge, which allows precise control over the motor's direction. H-bridges are widely used in robotics and motor control applications, making it possible to drive DC motors, stepper motors, and servo motors efficiently. An H-bridge circuit, as shown in the visual, consists of four transistors, typically a combination of PNP and NPN transistors, or P-channel and N-channel MOSFETs. By selectively activating pairs of transistors, current flows through the motor in one direction to rotate it forward and in the opposite direction to rotate it backward. When transistors 1 and 4 are turned on, current flows through the motor in the direction indicated by the red line, causing it to rotate in one direction. On the other hand, when transistors 2 and 3 are turned on, the current flows in the opposite direction, as shown by the blue line, making the motor spin in reverse. This configuration allows for precise bidirectional motor control, which is essential for applications in robotics, motorized vehicles, and automation systems. As we saw in the previous visual, an H-bridge is essential for controlling both the direction and speed of a brushed DC motor. While it is possible to design an H-bridge from scratch, for most robotics applications, it is more practical to purchase a pre-built motor driver module from marketplaces like Amazon, AliExpress, or local electronics suppliers. Any motor driver that meets the power and current requirements of the motors can be used. However, many low-cost motor drivers are not rated for 48 volts operation, which is the optimal voltage for the motors we are using. These motors can still operate at lower voltages such as 24 volts or 36 volts, but with reduced performance. At lower voltages, a higher current is required to produce the necessary torque, which can lead to wiring and overheating issues. Among alternative voltages, 36 volts is often a better choice than 24 volts, as it provides a good balance between performance and power efficiency. To control the motor speed and direction, two microcontroller pins are required per motor. One of the pins, a digital output pin, to toggle the motor's direction, clockwise or counterclockwise, and the second pin, a PWM, pulse width modulation, pin, to regulate the speed by adjusting the duty cycle. We will explore this motor control setup in more detail in the next slides. The scooter control unit is divided into two components. 1. The balance controller, and 2. The motor driver. The balance controller runs proprietary firmware and generates control signals to the motor driver to maintain balance and enable movement forward or backward. For our robot design, we utilize only the motor driver. We confirmed the pinouts by operating the scooter on a raised platform and connecting the pins to an oscilloscope for signal measurement, while a multimeter was used to identify the power pins. This allowed us to map out the pinout and understand the functional requirements. The construction of the motor driver is similar to many low-cost motor drivers available on platforms like AliExpress, with the main differences being the output power, maximum motor voltage, and the requirement for a 15 volts power input. Typically, low-power controllers step up a 5 volts input to 15 volts onboard, which allows them to operating with a 5 volts input only. Having determined the necessary signals and voltages, we proceed with preparing the schematic for the printed circuit board, PCB. At the heart of the PCB is the Teensy 4.1 microcontroller development board. This board is based on the ARM Cortex-M7 architecture, running at 600 MHz, and is an excellent choice for embedded control applications like ours. It is supported by the Arduino IDE, and the accompanying libraries are well documented and easy to use. While the Teensy 4.1 offers a powerful solution, it is not mandatory. Alternative microcontrollers, such as other Arduino-compatible boards, could fulfill the control requirements for this project. However, we selected the Teensy 4.1 primarily for its robust features and compatibility with MicroROS, a lightweight middleware designed for robotics, which we'll discuss in more detail in another video. One of the critical design considerations was the PWM frequency for speed control, as it is crucial to use a high-frequency PWM signal to minimize motor noise. We found it relatively easy to adjust the PWM frequency on the Teensy 4.1, which was a significant advantage over some other 32-bit microcontrollers we have worked with in previous projects. For controlling the motor drivers, we require 4 PWM-capable GPIO pins for speed control and 4 additional GPIO pins for direction control. However, to ensure future expandability, the PCB also includes 4 connectors for encoders, 2 Grove connectors for serial communication, and additional pinouts for potential future uses. Additionally, we incorporated an I2C-based IMU, inertial measurement unit, on the PCB to provide the necessary motion sensing capabilities. To display the status of the robot's firmware, we added a connector for an I2C LCD screen. The PCB, which includes the Teensy microcontroller and the step-up buck converter, is mounted on the front side of the MDF vertical plate, located beside the batteries in the middle compartment. The front side motor drive and the 48 volts to 5 volts DC converter are also mounted on the same MDF plate for easy access and organization. To accommodate the connection, the cable for the backside motor driver was extended to reach the PCB connector. Since the PCB was routed as a single-sided design, some jumper wires are visible on the top side, adding a DIY aesthetic to the assembly. Here we see the backside motor drive, the 48 volts to 19 volts converter for the Intel NUC computer, and the fuse box. The motor drive powers the rear motor, while the 48 volts to 19 volts converter steps down the voltage from 48 volts to 19 volts to power the Intel NUC, which handles high-level control and processing tasks. The fuse box ensures the safety of the system by protecting against electrical faults. All components are organized efficiently for easy wiring and maintenance. The main battery bank operates at 48 volts, which is suitable for powering the motors. However, a step-down conversion is required to power the controller board and the embedded computer, Intel NUC. To achieve this, 2 separate DC-DC converters are used. One steps down the voltage to 5 volts for the controller, and the other to 19 volts for the Intel NUC. A 100A battery isolation switch is mounted on the side panel, providing the ability to disconnect the power from the system when needed. For protection against high current draws, appropriately sized automotive-grade fuses are installed in the fuse box. The original battery charger is retained to charge the batteries, ensuring efficient and reliable recharging. Before we dive into the Teensy firmware that will enable the robot to move, it's important to discuss the control architecture. For simple linear and rotary movement, we can start with basic firmware that takes commands from a text-based user interface, a serial terminal, a joystick, or a keyboard. This firmware adjusts the direction or speed of the motors to achieve the desired movement. While this simple setup is effective for basic functionality, a text-based interface or direct control through a joystick or keyboard has its limitations in terms of flexibility and advanced features. However, I still want to cover this basic firmware, as it forms the foundation for understanding more complex systems like the Robot Operating System, ROS. ROS allows for much more flexible control, enabling features like autonomous movement, real-time feedback, and sophisticated path planning. By understanding the simple firmware first, we can better appreciate how ROS builds upon this foundation to offer a more dynamic and scalable solution for robot control. For our robot, the user needs to input values for both linear and rotary movement. These values can be in any range, but we use values ranging from -1 to 1. The user can control both the linear and rotary movement, with -1 representing full reverse or maximum rotation in one direction, and 1 representing full forward or maximum rotation in the opposite direction, without needing to worry about the actual speed, as that can be managed by the robot firmware. Any value between -1 and 1 for both linear and rotary movement will make the robot follow a curved path, depending on the combination of speed and rotation. This control system allows for intuitive movement, enabling the robot to adjust its speed and direction based on the user's input. For Teensy programming, we use the Arduino IDE along with the Teensy add-on. Instructions for installing both the Arduino IDE and Teensy are provided in the web links given in the description of this video. We refer to the diagram shown on the right side to correctly assign direction and PWM pins for all 4 motors. The pin numbers are shown in the PCB schematic. For example, pins 4 and 5 control left front motor. The maximum PWM value, linear and angular speed of the robot are defined as part of the configuration. All 8 pins are set to output mode, and the PWM pin's frequency is set to 20 kHz. This frequency helps eliminate motor noise, as mentioned earlier. The most important part of the firmware is the function defined as Move Robot. This function takes the linear and angular inputs provided by the user and computes the target velocities using the robot's actual maximum linear and angular speeds. The next step is to calculate the wheel velocities for differential drive. Once the wheel velocities are determined, the values are constrained to be within the maximum and minimum PWM limits for the Teensy. The following steps involve changing the direction of the motors and writing the corresponding PWM signal to the motor speed pins. It is important to note that the motors on the right side have flipped high and low signals compared to those on the left side. This is because the motors mounted 180 degrees apart will rotate in the opposite direction if the wiring sequence remains the same. To make the motors rotate in the same direction, either their wiring needs to be flipped, or the direction of rotation can be adjusted in the firmware. Adjusting the direction of rotation in the firmware is the better option, as it allows the actual wiring to remain unchanged. Our basic firmware is ready, but it can only function if the values of X and Z are provided. As mentioned earlier, there are several ways to provide these values, such as through a joystick, keyboard, or serial terminal, among others. For testing the firmware, we use the Arduino serial monitor and add the serial reading code within the main loop. The code snippet is shown in the top right corner. This piece of code reads the serial port of the Teensy and converts the received data into X and Z values. For example, if we enter 0.50 and click Send, the robot will move forward with half of its maximum linear speed. We have also declared 2 global variables, X and Z, both initialized to 0. Whenever the user sends new values from the serial terminal, these global variables will be updated, and the robot will continue moving according to the latest values until new inputs are received. We can now test the robot with the basic firmware by providing values from the serial terminal. The robot moves as desired, but there is a difficulty in entering the new values in the serial monitor and sending them one by one. The firmware can be extended to receive input from a wireless joystick or read radio control PWM signals and then move accordingly. It is also possible to connect a USB Bluetooth to Teensy and then connect PS4 controller and use that for moving the robot. However, all these solutions require more coding, and they are also specific for each type of the input device we use. In the next part of these tutorials, we will use Robot Operating System and see how using ROS makes hardware-software integration easy to realize highly capable robots with little or no programming. To make sure you don't miss the next videos, please subscribe and like the channel. If you have any questions, please post them as comments and I will endeavor to answer as much I could.